Hello students, in our previous class we discussed about the resistance and the factors on which it depends. Now let's revise that particular topic. Resistance, as you know, is directly proportional to the length. More the length, more is the resistance, and less the length, less is the resistance. But resistance, you know, is inversely proportional to the cross-sectional area, isn't it? Thinner the wire, higher is its resistance, and thicker the wire, less is its resistance. Now, let us combine these two and let's see what we get. Now, for these two, we write simply R, proportional, and you know the rule, isn't it? You have to multiply these two, no? Now, L into 1 is L, and in the denominator you have A. And you know, in order to replace it by is equal to, you have to put a constant also, isn't it? That K is the constant of proportionality. K here is a constant as usual, and this constant in this case is denoted by rho, which is the specific resistance or resistivity. That's why our formula becomes now R equals to rho L by A. So this is the formula for the resistance in terms of length and cross-sectional area. Of course, resistivity is there. Okay. Now today in this class we are going to learn about this particular topic, and this is the specific resistance. So today's topic is specific resistance or resistivity. Now, this formula will give us the definition of the specific resistance. Let's see how. Now, in this formula, okay, if we take L equals to 1 and A also equal to 1, what does it mean? That means we are taking a wire whose length is unit, like 1 centimeter or 1 meter, unit length, okay, and whose cross-sectional area is also 1. This value of this area is also 1, like 1 centimeter square or 1 meter square, okay. So in that case, okay, let's see what we get. So R now is equal to rho, it is rho, value of L is 1, value of A is also 1. So when you multiply, you get this, no? R equals to rho. So what is then specific resistance? Specific resistance is the resistance of the wire having unit length and unit cross-sectional area. And that's how we define specific resistance or resistivity. It is defined as the resistance of the wire having unit length and unit cross-sectional area. So this resistivity depends on the material, okay, nature of the material, okay. It is different for different material, like copper has different value of resistivity, okay, silver has different value of resistivity. Now the SI unit of rho, that means specific resistance, is ohm meter. Till now you have seen what resistances are, what are the factors on which a resistance of a conductor depends, its unit and all that, isn't it? Now let's see the different types of combination of resistances, okay? The two main types of combination of resistances are so these are the two types of combination. Now let's take one by one. Okay, let's suppose that this is a resistance of value R1 and this is another resistance of value R2, and this is a resistance of value R3. There, as you can see, they are not combined at all, isn't it? But if we combine them in end to end, okay, like the left of this is connected to right of this, similarly, if we connect the resistances in end to end fashion, so this kind of combination is known as series combination. All right. Let's say the whole combination is connected to a source of current, okay, and because of that, current I is flowing through the three resistances. Okay, now since these three resistances are in series, the same current will pass through each of the resistance. All right. Okay, let me call this point as A, this point as B, C, and this point as D. Okay. So here our task is to find out, okay, a single resistance which is equivalent to the three resistances. All right. As you can see, the current is flowing from A to B, that means in this direction from left to right, okay? So A is at higher potential than B, B is at higher potential than C, similarly C is at higher potential than D, alright? Now, in this case, although the same current is flowing through all the resistances, okay, the potential difference will be different for the three resistances. So we take that different thing, okay, to start with. Since V is different, so what is V here? It's the potential difference. V equals to IR, okay, where V is the potential difference, I is the current, R is the resistance. Okay, so we apply this formula for the three resistances. Now V is the potential difference. Now for this, what is the potential difference? It is VA minus VV, no? Potential at A minus potential at B. So this formula for the first one becomes VA minus VV equals to, what is the current through R1? That's I. And what is the resistance? R1. And for the second one, potential difference is VV minus VC, that's equal to I R2, and for the third one it is VC minus VD equals to I R3. Alright, now let's combine the three equations. Okay, so here VV plus and VV minus gets cancelled, similarly VC plus and VC minus gets cancelled. So what are the things left out here? VA minus VD, that's equal to, now we are adding these three, no? That's why, so I'm taking I common. So what will be left here? R1 plus R2 plus R3. Let this be equation number 1. Okay? Now, let's imagine that in between the points A and D, okay, we have a single resistance, okay, whose value is R. So this R is equivalent to the three resistances, okay. So we write if R now we apply the same formula V equals to IR for this also, okay. So in the exam you may not have to, you don't have to draw this particular diagram. Okay, this is for you to understand only. Now the rest of the thing will remain the same, current will remain the same. Okay, only the resistance is different out here. So what is the potential difference between A and D? It is VA minus VD equals to, what is current for this one is I, what is resistance for that one? Okay, this is R. Let this be equation number 2. Now look at these two equations. We find their left hand side to be same, isn't it? Okay, let's compare equation 1 and 2. They have left hand side same. So since left hand sides are same, right hand side must be equal, isn't it? That's why so when we compare these two, we get this to be equal to this. No, because left hand sides are equal. So IR is equal to this, which is I into R1 plus R2 plus R3. So I on both sides can be cancelled. So finally you have the equivalent resistance R is equal to R1 plus R2 plus R3. So this is the formula for the equivalent resistance in case of series combination. Okay, so this is the algebraic sum of all the resistances. Now let me give you one very simple example. Okay, if R1 equals to 1 ohm, R2 equals to 2 ohm and R3 equals to 5 ohm, then what will be the value of the equivalent resistance? If this is 1, this is 2 and this is 5, what will be the equivalent resistance for the 3? It will be R equals to, first we'll write the formula and then the value 1 plus 2 plus 5, that's equal to 8 ohm. Isn't it? So this way we find the equivalent resistance when the resistances are connected in series. Okay. Now, okay, there are two things for you to remember regarding the series combination. Number one, the same current flows through all the resistances which are connected in series. That's number one. And number two is this. Whenever resistances are connected in series, the value of the equivalent resistance will be more than all the resistances, isn't it? So this 8 is more than 1 also, 2 also and 5 also, isn't it? So whenever resistances are connected in series combination, we get a higher value of the resistance. That means if we need higher value of the resistances should be connected in series combination. The second type of combination is parallel combination. Although we use the word parallel, okay, that does not mean that the resistance are to be connected in parallel fashion. Okay, so although the term parallel is used here, it does not mean that all the resistances should be parallel to each other. Although we show them by drawing the parallel resistances, but that is not the meaning of this parallel combination. Okay, parallel combination is that kind of combination, okay, where all the resistances are connected in such a way that they have two common junctions. Okay, like this one. Let's see, this end is connected at this point and this is connected to this one also. Similarly, this, okay, so you can see this P and Q are the two common junctions of the three resistors, isn't it? That's why this kind of combination is known as parallel combination. If I draw the two resistances like this one, you can see that these two are not geometrically parallel to each other, isn't it? But according to the name of the combination, they are in parallel combination. Why parallel? Because these two resistances have two common junctions, isn't it? That's why this is also a parallel combination like this one. Now in this diagram you can see there are three resistances R1, R2 and R3 which are connected in parallel combination. So once again, why those three resistances are in parallel combination? Because the three resistances have two common junctions at A and B. That's why that is a parallel combination. Now let's say I is the current, okay, drawn from the circuit, okay. So there is a source, that means a cell somewhere here, okay. From the cell comes the current I, which is the main current. But when this current comes to the point A, okay, the current gets divided, isn't it? So a part of the current will flow through R1, and second part of the current will flow through R2, and the remaining current will flow through R3, okay. So let's say the current flowing through R1 be I1, through R2 be I2, and through R3 be I3. So I1, I2 and I3 are the electric currents passing through R1, R2 and R3, okay. And when these three currents meet at the point B, okay, they will form the total current I, okay. Now the potential difference. Now let's find out the potential difference for R1, R2 and R3 separately, okay. Now for R1, isn't A one end and B the another end? So what is the potential difference for R1? It is VA minus VV. Why VA minus VV? Because A is at higher potential and B is at lower potential. Why is that so? Because current is flowing from A to B. So if this is the potential difference for R1, what is the potential difference for R2? So for that you have to see the two ends, isn't it? So what is one end? A. Which is the other one? B. So what is the potential difference for R2? Again VA minus VV. Similarly, what is the potential difference for R3? It is VA minus VV. So what do you see here? All the three resistances have the same potential difference. Okay. Now in the previous case, that means in case of series combination, what was same? Current was same, isn't it? And in this case, that means parallel combination. What is same or common? It is the potential difference. And what is different out here? It's current, isn't it? That's why we'll start with that different thing. Okay. So according to Ohm's law, we know that V equals to IR, isn't it? So what is I equal to then? It is V divided by R. Okay, let this be equation number 1. Now we'll apply this equation, okay, to all the three resistances. Now I for first one is I1 equals to, now what is V for the first one? It is VA minus VV. And what is resistance for the first one? R1. Now similarly for the second one we can write I2 is VA minus VV, it is the same, and it is R2. So like in the previous case, we are going to add, okay. So when we add all the three relations, we get I1 plus I2 plus I3 equal to, now we have to add these three. So here the numerator is common, isn't it? So I'm taking out the common just to simplify. So when this is taken out, you have only 1 left, isn't it? So 1 by R1. Similarly here, 1 by R2 and 1 by R3. Okay, and you know, when the 3 currents meet at this point, that will form the same total current I, isn't it? So what is the sum of the 3 currents? It is I. That's equal to, the rest of the thing will remain the same, VA. Let this be equation number 2. Now in between the points A and B, okay, instead of the 3 resistances, suppose if you have a single resistance whose value is R, then this R will be called the equivalent resistance, isn't it? That's why, okay, I'll do the rest of the things out here. Now we'll use the same formula given by equation number 1. Okay, now I in this case also will remain the same. So I is equal to, now what is the potential difference between these two? Because it's given by V, no? It is VA minus VV, and denominator we have the resistance. What is the resistance here? R. Let this be equation number 3. Now look at equation number 2 and equation number 3. They have left hand side same, isn't it? So since they have same left hand side, right hand sides must be the same. Now we get this. Okay, first I'll write this, which is VA minus VV by R equals to this one, VA minus VV into 1 by R1, 1 by R2 and 1 by R3. So here VA minus VV is common in both the sides, isn't it? That's why we can cancel these two. So what is left? 1 by R equals to 1 by R1 plus 1 by R2 plus 1 by R3. So this is the formula for the equivalent resistance, okay, when the resistances are connected in parallel combination. Now let's see how the formula for the parallel combination can be used. Okay, now let's say R1 is 2 ohm, okay. Now since the 3 resistances are connected in parallel combination, we use this formula. One by R is 1 by, now 1 by R is what we need to find out, isn't it? R1 is 2, R2 is 3 and R3 is 5. Then you know what to do with this, no? We have to take the LCM. The LCM for 3 is 30. 2 into 15 to 30, so 15 ones are 15, 3 10s are 30 and 5 6 are 30. 1 by R is, now we add, no? 25 and this is 31, isn't it? Divided by 30. Now when we cross multiply, we get this 31R is 30 and finally R is 30 by 31. Now here you can see denominator is more and numerator is less, isn't it? When we divide this, the value of R will be less than 1. Okay, so here it is 0.97. This is less than, so R here is less than 1. Okay, but look at the original values of the resistance. So one was 2, the other one was 3 and the last one was 5. So you see the equivalent resistance in case of parallel combination, okay, in this case is less than 1, and that is less than 5 also, less than 3 also, and less than 2 also. So which is the least here? Least resistance is 2, isn't it? So the equivalent resistance in this case is less than the least of the resistances. Okay, so there are again two things for you to remember. The first one is this: when the resistances are connected in parallel combination, okay, the value of the equivalent resistance will be less than the least of the resistances. Okay, so what does that mean? So if you want to have a lower value of the resistances, okay, then you have to combine the resistances in parallel combination. Number 2, what is common in case of parallel combination? The potential difference. So in case of parallel combination, all the resistances have the common potential difference. All right, and that is the reason why all the household appliances, okay, are connected in parallel combination to the alternating voltage. Now why is that done? Because if we connect all the appliances in parallel combination, they all will have the same potential difference. That is the potential difference of 220 volt, and hence they will work properly and they will work fully.